Hello everyone, I'm Yuga Ebine from Waseda University in Japan. Today I'll be presenting my research titled Evaluating the End-to-End Impact of Force Localization Attacks on vSLAM-Based Autonomous Drones. ORB SLAM3 is an open-source algorithm that performs self-localization based on video footage. While ORB SLAM3 is widely used for drone localization, its security vulnerabilities are largely unexplored. Previous work has focused on improving its performance, not assessing its security. Similarly, most drone vulnerability studies target only communication systems, overlooking sensor-based attacks. This leaves a critical research gap. No end-to-end evaluation of the sensor attacks on drones guided by ORB SLAM3. Our research directly addresses this gap. Here, I'd like to show you a demonstration of the ORB SLAM3 system in action. On the bottom of the screen, you can see the video feed from the camera mounted on the drone in our simulator. The top right view shows how green feature points are extracted from the camera feed. And in the top left view, you can see the final output of ORB SLAM3. ORB SLAM3 operates by calculating the brightness difference between pixels in each input camera frame. It extracts the pixels with large differences as these green feature points and uses them to perform environmental mapping and localization. This simulation environment is the same one we will use for the live drone flight experiments later. In the ORB SLAM3 output, the blue box represents the drone's current position at each moment, while the surrounding red and black point clouds map the obstacles in the environment. This slide provides an overview of our attack process. The purpose of this study is to enhance the safety and security of autonomous flight by proposing novel attack techniques and their corresponding defense strategies. The attack involves creating and projecting an adversarial video into the drone's path. We implemented this in our simulator to evaluate its impact on drone control. Our goal is to induce localization errors in ORB SLAM3 to disrupt the drone's flight. As the figure on the left illustrates, the adversarial video manipulates the drone's estimated position, causing it to deviate from its intended path. Here is the footage of the attack in our simulator. I will provide more details later, but essentially we have a drone flying inside a warehouse with an adversarial video placed on its flight path. When the drone's camera recognizes this video, it causes errors in its self-localization, making it possible to disrupt the drone's behavior. Here I will provide an overview of the adversarial video used in our attack. To induce misrecognition in ORB SLAM3, we focused on its feature point extraction algorithm, known as FAST. In simple terms, the FAST algorithm compares brightness differences between pixels in the camera frame and identifies a point as a feature if the difference exceeds a certain threshold. Therefore, to make our adversarial video efficiently recognizable as features, it needed to certain many black and white boundaries. To achieve this, I used fractal noise. I generate a random-looking image like the one shown by taking a grayscale image like fractal noise and binderizing it, turning pixels to either black or white based on the brightness threshold. We then use a video of this pattern sliding across the screen as our adversarial input. The slide provides our experimental overview. To verify the effectiveness of our attack, we conducted both a camera-only evaluation and an end-to-end evaluation. The camera-only evaluation specifically involved assessments using both a simulation and a real-world commercial camera. This slide outlines our camera-only evaluation method. First, we assessed the adversarial video's input on ORB SLAM3 localization using both simulated and real-world cameras. In the experiment, we projected video onto a 0.9 by 1.2 meter screen We then varied the camera to screen distance from 0.8 to 1.3 meters. At each interval, we recorded the coordinate data from ORB SLAM3 to calculate the total travel distance of its estimated position. Let's look at the results from the real-world camera evaluation. Even though the physical camera was stationary, the adversarial video had a significant impact. At a distance of 0.8 meters, the video caused the ORB SLAM3 position estimate to drift upwards by approximately 231 meters. The figure on the right visually confirms this. It shows the estimated position moving from the initial red box to the final green box. This is footage from a camera-only evaluation in a simulator. Just as humans can feel a sense of self-motion when watching a video of a moving landscape, ORB SLAM3 perceives it in a similar way. By recognizing the downward scrolling video, it incorrectly concludes that it is moving upward, like this. This slide shows our end-to-end attack evaluation in the simulator. In our setup, a drone flies a straight, predefined path within a warehouse. It navigates using ORB SLAM3 for localization and a pure pursuit algorithm for control. For the attack scenario, we place a screen in the drone's flight path. We then evaluate the impact by comparing the drone's trajectory in both attack and non-attack conditions against the intended path. This slide shows end-to-end results for the baseline non-attack scenario. In this case, localization was successful and the drone's control remained stable. The left figure shows a side view of the estimated trajectory from ORB SLAM3. The right figure compares the predefined path, the localization estimate, and the ground truth. The blue estimate line cuts off because the drone exits the 60-meter warehouse, causing tracking loss. We disabled collision detection to ensure clarity. The error of a few meters between the estimate and the ground truth is consistent with the known accuracy of ORB SLAM3. Despite this, both passes clearly show the intended forward trajectory. Here are the end-to-end results for the attack scenario. For simplicity, I'm showing the results from our most effective test case. The adversarial video successfully manipulated ORB SLAM3, causing its estimated position to drift upwards. You can see this upward shift inside the pink box on the left. Because the drone trusted this faulty data, it tried to correct its position by flying downwards, ultimately descending by about 70 meters. Here is the simulation video of the actual attack in action. Initially, the drone takes off and proceeds forward smoothly. However, upon recognizing the adversarial video, you can see its estimated position begin to shift slightly upwards. Then, as the drone gets very close to the video, a tracking loss occurs. The drone's control system then operates based on the last available position estimate, the one that has just been shifted upwards. For clarification, tracking loss refers to a state where the localization and the environmental mapping functions stop working for some reasons. Here I will introduce our proposed defense methods. The first method is the integration of other sensors, such as LiDAR and an IMU. We believe that by integrating these sensors and performing sensor fusion, it would be possible to detect when errors are occurring in the localization estimate. The second method is the removal of dynamic objects from the input video. Since the adversarial video is a consciously moving element in the input feed, we believe that by removing dynamic objects, the content of the adversarial video would not be recognized by the system in the first place. For future work, we will extend our evaluation to other visual SLAM systems and implement a more realistic drone control model. We also plan to move beyond the simulator to test these attacks on real-world zones. Finally, our key next step is to implement and evaluate our proposed defense methods. In conclusion, we proposed and validated a vSLAM attack that arbitrarily steers system localization. Our attack uses projected adversarial video to induce vSLAM localization errors. Camera-only evaluation yielded a max localization error of 231 meters. In the end-to-end evaluation, this error arbitrarily steers the drone's flight. That's all. Thank you for listening.